will generate an emergent fractal structure, and the ordering of the spins will only live on the boundaries of these emergent structures. This work was done with Nick Crawford, a math professor at Technion. And so, you probably had guessed that the results in this paper is going to be rigorous, but we will focus on the physical intuition instead of the mathematical details in this talk. For those interested, I will leave the archive reference on the top right corner. Okay, so first of all, let us quickly review what ordering or phase transitions mean in the classical sense. In the most general sense, a phase transition occurs when the macroscopic properties of a system abruptly changes as one variational parameter changes. Now, usually this parameter corresponds to temperature, and so the change of properties signals a distinction between the low temperature phase and the high temperature phase. And thus, there is some critical transition temperature, Tc, that separates the two phases. Now, of course, the term distinct properties is very vague. And so if we want to be a bit more concrete, one way is to determine whether the symmetry of the system is broken or not. At low temperatures, we expect a symmetry broken state, where only one of the ground states of the system is chosen, while at high temperatures, the symmetry is preserved. More specifically, what I mean is that in general, systems possess some non-trivial global symmetry, and which further implies that the system has multiple symmetry-related ground states. At low temperatures, the system will choose one of the ground states to settle into, and thus breaking the symmetry, while at high temperatures, the system is a mixture. So if we were to use the famous Ising model as an example, a typical high temperature configuration can be shown here. The spins at each lattice site can point up or down, and the correlation between distinct spins is exponentially decaying. Now, because of the Z2 symmetry, the Ising model has two ground states, one of which is when all the spins are pointing up, and the other is when everything is pointing down. Notice that the ground states map to one another under Z2 symmetry, but they themselves do not preserve the Z2 symmetry. Therefore, roughly speaking, at low temperatures, choosing one of the two ground states to settle into indicates spontaneous symmetry breaking in Z2. Now, if we wish to be a bit more concrete, then we would start with a Hamiltonian defined over all spin configurations, where the plus and minus 1 indicates whether the spin is pointing up or down. And to determine whether the symmetry is broken or not, we would look at a local order parameter, such as the magnetization of at some lattice site. At high temperatures, this magnetization is 0, which preserves the spin flip symmetry, while at lower temperatures, it's non-zero, breaking the Z2 symmetry. Okay. Now that we have a basic understanding of classical systems, let me get started with the actual talk. So the outline is roughly as follows. I'm going to first give you the motivation of this talk. I will give you an explicit definition of the model that we're going to be talking about. From that, I will show you that the model has multiple zero temperature ground states, which means that there is a phase transition. I will further look at the finite temperature system and show that there is a transition temperature independent of the disorder strength, which means that even if the system has infinite disorder, the system is still stable. It has a transition temperature independent of how much disorder I add. And finally, because of the BKT phenomenon, 2D systems and higher dimension systems are a bit different, and so I will talk about 2D systems separately. So for the majority of this talk, it's going to be 3D and above. And then finally, I'll give a summary of this talk and some outlook on future projects. Okay, so motivation. So in general, disorder is an undesirable trait that disrupts the ordering of systems. An extreme example is the Emery-Ma phenomenon, which basically states that any ordering is destroyed in low dimensions. So for arbitrarily weak disorder, there is no ordering in 2 dimensions and below if the system has a discrete symmetry, such as Z2. Similarly, for 4 dimensions and below, there is no ordering if the system has a continuous symmetry, such as a U1. And this statement has in fact been rigorously proven for models such as the random field Ising model, the random field XY model, and their quantum analogs. Now, even in higher dimensions, so that Emery-Ma doesn't really apply, there still generally exists a critical disorder strength above which there is no finite transition temperature. The same also applies for lesser known models, which people have kind of sought up to partially circumvent Emery-Ma. So if we were to plot the phase diagram of these systems, where the x-axis is the disorder strength, the y-axis is the temperature, then these systems would have a transition temperature given by the green line. So below the green line, the system has ordering, but at higher temperatures, there is no ordering to the system. Okay. Now, this begs the question of whether there exists any system that exhibits different behavior, right? Can we find a disordered system that has a transition temperature something like the red line, right? So even though the disorder may decrease the transition temperature, maybe the asymptotic limit can still be finite. Does such a system exist or not? And in this talk, I will try to convince you that the answer is yes, and the system can actually be naturally constructed. As you can see from this phase diagram, we call these systems bilayer, and the name will be apparent shortly. Okay. Now, so theoretically, these so-called bilayer systems are interesting, but are they realistic? It turns out that they can be naturally found in twisted bilayer systems. For example, recently, there has been experimental evidence of the time reversal symmetry breaking when bilayers are twisted so that the relative orientation is near some critical angle. In my previous work with my advisor, Steve Kivelson, we found that such an effect can be naturally induced by interlayer disorder. Now, of course, in our previous work, we primarily focused on the weak disorder regime since the interlayer interaction is usually much smaller than the in-plane interaction. So one may wonder whether it's even relevant to study the strong disorder or not. And later on, I will show you that, yes, it is relevant and it's in fact pretty important. And we also mentioned that, after some literature search, the model that comes up in this talk also shows up in the study of frustrated antiferromagnets. These have been studied pretty extensively in the 80s and 90s, especially by Christopher Henle. Okay, so the following equation gives the Hamiltonian of our bilayer system. The first term basically describes 2 independent XY models, where each layer represents, a superconductor. Theta plus and minus are the XY spins of the top and lower layer. And I have normalized the coupling strings to 1, so that the in-plane coupling strings is just 1. The second term indicates the interlayer interaction. Notice that it only depends on the phase difference of the 2 layers. Alpha is going to be the random phase given by disorder, and it's uncorrelated from site to site with an equal probability of being 0 or pi. H is just going to be the disorder strength of this system. Now, because of the symmetry, it's actually more convenient to rewrite this Hamiltonian in terms of the average phase and the phase difference. Now, if you look at the definition of the average phase and took it literally, you would say that, okay, this definition is ill-defined because it's not 2 pi invariant, right? Because I could take the top layer, theta plus, change it by 2 pi, but my average phase only changes by pi. So you can see that there's a subtlety here. In our detailed paper, we showed that we can actually define this change of variables in an invariant manner, and obtain the same results. But so for the sake of simplicity, we will neglect this subtlety in our talk. Okay, so using the new variables, we can rewrite the Hamiltonian as follows. You don't have to understand it just yet. We will dissect this Hamiltonian term by term. Okay, so despite being motivated by bilayers, the Hamiltonian is actually well-defined in any dimensions. In fact, in any graph, right? One could imagine that on any vertex of an arbitrary graph, one has 2 degrees of xy spins. The interlayer interaction would then just be an on-site interaction between the 2 spins that depends only on the phase difference. Now, for the majority of this talk, I will focus on 3D and above, since there's this subtlety due to the BKT phenomenon.
Excuse me?
Yes.
How do you define del R prime on the graph?
So if I have a random graph, that means the edges are well defined, right?
Okay.
So the phase gradient is along those edges.
Okay.
And also, maybe let me ask a question to clarify the premise. So earlier in the intro, you said with disorder, there's no phase transition, like briefly summarized, but those are those statements occur when your randomness couples to the field. This breaks the symmetry directly.
Yes.
But at least in this very setup, there is some U1 that is fully preserved, no disorder, right?
Yes, that's true. But I'm only looking at the ordering that's coupled to the disorder. So basically, right now, the disorder is coupled to the phase difference. So I will be looking at whether the phase difference has ordering or not.
Okay, thank you.
Right. If there's something like the average phase is not coupled to the disorder, of course, it might have ordering. That doesn't really change anything. Okay. Okay, so previously, I mentioned that the interlayer interactions are usually much smaller than the in-plane interactions. So, why is the strong disorder even relevant? Well, remember that in our model, we have 2 parameters. One parameter, kappa, is basically the in-plane interaction. And then we have the disorder strings, H, where the disorder is uncorrelated from site to site. Now, in reality, there's actually an additional parameter given by the correlation lengths of disorder. Now, if one wants to map reality to our model, we would need to choose a unit cell of linear lengths, psi, so that our neighboring cells are effectively uncorrelated. In this case, because the disorder term acts on-site, the scaling would be a bulk effect, while the in-plane coupling is a boundary effect, so it scales like the boundary. Now, that means if our disorder correlation length is sufficiently large, even if our raw disorder term is small, the effective disorder is going to be much larger than our effective in-plane coupling. So in this sense, we can still be in the strong disorder regime. Okay. Okay, starting from the Hamiltonian, let us attempt to find the 0 temperature ground states. Now, first notice that because alpha is only 0 or pi, that means the interaction term is just a fancy way of writing plus or minus cosine phi. This means that there is a Z2 degeneracy, given by the map phi to minus phi, and thus the usual U1 symmetry of the phase difference is broken down to a Z2 symmetry by the disorder term. In that sense, I will be looking for Z2 degenerate ground states. Now, since we are in the regime where disorder strings is much larger than 1, it's natural to suspect that the phase difference must be very close to the random phase alpha for any site. Or equivalently, I would be assuming that the deviations, delta phi, are very small. Now, using this ansatz, we notice that the interlayer interaction term is quadratic to lowest orders. Now, we will further assume that the average phase is long-range ordered, which we will justify in the next section, later on in this talk. Using delta phi as a small parameter, we can expand the first term in power series of delta phi. And because the disorder term is quadratic and much larger than the first term, we only have to expand it up to linear orders. So if we were to complete the squares, that means our Hamiltonian is some quadratic term like this. Now, since the Hamiltonian is quadratic, it's clear that the ground state is given by the following value. Now, notice that this deviation has a scale of 1 over h. So at least our ansatz is self-consistent in the large disorder regime. Now, let us further plot what the ground state looks like. The left diagram shows the clusters in real space. The green clusters contain sites with random phase 0, and the red contains sites with random phase pi. The right diagram will show how the ground state of the phase difference will look like in spin space. Now, deep within the green clusters, since all the nearest neighbors have the same random phase, our equation tells us that delta phi is exactly 0. In spin space, this means that the phase difference must align perfectly with the random phase, as shown here by the green arrow. The same thing occurs deep within the red cluster, and the phase difference points along the red arrow. However, at the boundary, things are a bit different. For example, if we were looking at the green boundary, because there is a non-trivial phase gradient, that means our equation tells us that delta phi is positive. So in spin space, there is this slanting away from our random phase alpha. You can do the same thing for the red boundary and show that there's this symmetric slanting in the same direction. So by considering the ground state solution, we see that there is a non-trivial ordering in the y direction in spin space. Now, this is one of the Z2 degenerate ground states. The other one should be where the ordering slants downwards in the minus y direction. Okay, and also you should notice that from this analysis, the ordering lives only on boundaries. Okay, so before I move on, I just want to emphasize that this is basically the heart of the talk. If you chose to remember one thing from this talk, this is the diagram that you should have in your mind. Okay, so we can also plot the ground state in the original spins, the top and bottom layers. And it would look something like this. So the purple and orange arrows represent the top and bottom layers. And so deep within each cluster, the spins are either perfectly aligned or perfectly anti-aligned. But along the boundary, there is some interesting behavior. Okay. Now, hopefully now I convinced you that the ground states occurs only on boundaries. But there's this interesting question that comes up. So for example, what if we were to try to compute the average magnetization of our ground state? It would be something like the summation of all the signs divided by the bulk value. Now, because our slanting only occurs on the boundaries, that means the summation only gives a boundary contribution, but we're dividing by a bulk. So you would guess that it's a 1 over L contribution, and so it should vanish in the thermodynamic limit. But however, I'm going to just tell you that the boundary is actually proportional to the volume because these clusters are fractal-like in nature. They're not really regular. They're irregular, I would think. In this sense, the average magnetization is going to be non-zero even if we take the thermodynamic limit. Okay. Now the next question is, why is our disordered model so different from the standard way of construction? Like, what makes it so different? For example, there is something called the RFO2 model, which basically has the same disorder term, but there is only one single XY model in our definition. As before, if we were to plot the phase diagram of this RFO2 model, then the transition temperature would look something like this. Now, if we were to compare this with our bilayer Hamiltonian and ignore the average phase for the moment, we notice that the only difference is that the RFO2 model doesn't have this extra 1/2 factor in our bilayer Hamiltonian. This means that if we were to repeat the same process, we would find that the RFO2 model has a ground state given like this. And because the gradient of alpha is only 0 or pi, that means it's always going to be 0 no matter what. In contrast, our bilayer Hamiltonian has this 1/2 factor, so it's non-zero along boundaries. Okay, so generally speaking, the critical transition temperature is on the same scale as the size of the zero temperature order parameter. This is especially true in superconductors, where the zero temperature gap is usually defined. However, as you can see in our system, the ground state scales like 1/h. So, okay, yes, there is a non-trivial ground state at large disorder, but maybe the transition temperature is asymptotically 0. Maybe the phase diagram is something like this. If so, then this system would be much less interesting. Fortunately, the actual phase diagram is going to be given by this red line, and I will convince you right now. Okay, so looking at finite temperatures, again, we will be focusing on the regime given by these parameters, right? We are in the large disorder regime and at low temperatures, but not zero temperature anymore. Now, within this regime, I can still assume the ansatz that my deviations are small because we are in the large disorder. In this case, the disorder term is still quadratic up to lowest orders. Now, the only difference is that I'm not going to be assuming that the average phase is long-ranged order now. Instead, I'm going to keep it as a degree of freedom in our Hamiltonian. But notice that I can still use delta phi as a small parameter. So I can still expand the first term up to linear orders in delta phi. If I were to do that, what my Hamiltonian will look like is something like this. There's this first term that depends only on the average phase, while there's this second term that depends both on delta phi and the average phase theta. Notice that the second term is actually quadratic, which basically tells us is that if we were to fix the average phases, then my delta phi has a conditional probability, which is Gaussian. It has a mean given by this and some standard deviation. Okay, so all this fancy writing really just tells me that if we want to compute the thermal average of delta phi using the bilayer Hamiltonian, it would be equivalent to replacing delta phi with its conditional mean and computing the thermal average with respect to this effective Hamiltonian. In this sense, we only need to study the effective Hamiltonian, and if the effective Hamiltonian has a finite transition temperature, then so does delta phi. Okay, so now let's focus on the effective Hamiltonian. Now, before I explain all the details, notice that the last term has this overall factor of 1/h. And thus, in the large disorder limit, the first two terms are going to be what determines the transition temperature. Visually, if we partition the lattice into red and green clusters, so basically green are the lattice sites with random phase 0, and red are lattice sites with random phase pi. Then the first term is just the standard XY model on the green cluster, while the second term is just the XY model on the red cluster. Now, at the 0th order level, the two clusters are perfectly independent, and thus we really only need to focus on one of them to determine whether there's a phase transition or not. Okay, so recall that alpha is equal to 0 with probability 1/2. And so if the site percolation threshold of my underlying graph is lower than 1/2, then the green sites are going to percolate, and there's going to be a unique, infinitely large green cluster. In this case, the thermodynamic limit of the XY model is going to be well-defined, and so there's going to be a well-defined phase transition with a temperature that's independent of the disorder strength. In particular, this inequality is going to hold for the cubic lattice in 3 dimensions and above, and thus we can see that the average phase has long-range ordered at finite temperatures regardless of disorder strength. Okay, now from this perspective, we see that each cluster is long-range ordered and can be viewed as an independent global XY spin. The next question is, what is the relative orientation between the two clusters? Now, this is where the first order term comes into play. Indeed, the main feature of this first order term is that it only cares about the gradient of the average phase across different clusters. And so, in a sense, the effective Hamiltonian is analogous to the following clean Hamiltonian, where the first two terms correspond to independent XY models, and the last term is just a simple proxy which preserves the symmetries of the effective Hamiltonian. After this visual simplification, it's clear that the clean Hamiltonian has a Z2 degeneracy, where either the two clusters are going to be aligned or anti-aligned. When they are aligned, that means the ground state is when the states are slanting upwards, and when they are anti-aligned, then the ground state of the phase difference slants downwards. So these are the Z2 degenerate ground states. So everything I talked about so far was in 3 dimensions and above. The main reason is that I needed the site percolation threshold to satisfy this, crucial inequality. However, on the standard square lattice, this does not hold. In fact, this does not hold on any planar graph. And so you would say, okay, this is interesting and all, but it's not going to work for 2D systems. However, if we were to slightly modify our planar graph and add next nearest neighbors so that the underlying graph is 2-dimensional but not planar, then the inequality would hold again. Each infinite cluster would then have quasi-long-range order, and so we can at least prove that the system is infinitely quasi-stable. What I mean by that is that below this transition temperature, the system has at least algebraically decaying correlation functions. Whether there is actual long-range order is an open question. Okay, so now let me actually try to answer the open question. Are 2D systems actually infinitely stable, or are they only quasi-stable? Well, I don't have an answer for the disordered systems, but let's look at the clean system for now, since I've shown you that the effective model is basically can be simplified to the clean system. What previous literature tells us is that the interlayer interaction is always relevant in the RG sense, and thus we should always have long-range order if the system orders. Now, although this is a non-rigorous result, it matches numerics where only a single phase transition has been observed. Mathematically, it has been proven in similar systems that long-range order must occur at least on the scale of 1 over h. So, so far so good. All the literature seems consistent. Now, indeed, if we were to plot the phase diagram again, where the x-axis is temperature and the y-axis is some local order parameter, what previous literature tells us is that the long-range order occurs at some finite temperature, and so universality generally implies that the magnetization should be substantial very quickly below the transition temperature. It should follow the curve of something like this. Now, however, in our paper, we can actually prove that the order parameter should satisfy this upper bound, which basically states that the magnetization is exponentially suppressed by the ratio of temperature and this 1 over log h scale. So in the large disorder limit, so that 1 over log h is much, much smaller than 1, we would see that the magnetization should be upper bounded by the red curve. And so there seems to be a contradiction between the black curve and the red curve. Okay, from this observation, we conjecture that long-range order occurs on the scale of 1 over log h, which means that there is an intermediate massless phase despite having Z2 symmetry in our system. This, of course, applies to both the clean system and the disordered system of our bilayer Hamiltonian. We can then speculate that such an intermediate phase hasn't been seen in numerics due to the extremely slow logarithmic decay. Okay, so in summary, what we have shown is that there exists a class of physically motivated systems with the following properties. In 3 dimensions and higher, the system exhibits long-range order at temperatures independent of the disorder strings. This is because the system has the sites percolate or relative to disorder. On planar 2D graphs, we don't have this stability anymore because there is no percolation. However, if we were to modify the underlying graph so that the systems are non-planar 2D, then I know that the systems are at least quasi-long-range order. Whether they are long-range order or not is an open question, but due to our upper bound, we can conjecture that the long-range order occurs on the scale of 1 over log h. Okay, so before I end this talk, I want to introduce an interesting variation of this problem. As we have shown in this model, if we have Z2 disorder, so that the random phase chooses either 0 or pi, then we have infinite stability. But what if we have U1 disorder instead? What if the random phase can be any value along my circle? Can similar conclusions be drawn? Can the phase difference still be infinitely stable in 2 or 3 dimensions? If so, then this would be an interesting counterexample of the Emery-Ma phenomenon. Okay, thank you for listening to my talk.
Thank you. Do you have any questions?
Yeah, so I guess the magic of your paper is really like the domain wall of alpha is fractal in some sense.
Yes, yes. The boundary has to be proportional to the volume, which you can actually prove. That's why it's an emergent fractal structure. I haven't put, like, the fractal structure isn't put into the Hamiltonian. It occurs when the temperature is sufficiently low.
Is there any intuition, like arguments, or yeah, because I mean naively, like if you're on, like, for example, cubic lattice where your theorem applies, I would imagine that the boundary just looks like some random shapes, like being on a 3D cube. Like what's the what can I visualize this very intuitively?
Yes. So forget about the Hamiltonian for now. Just
Yeah.
think about the disorder. So disorder is either 0 or pi, right?
Yeah.
So there's no Hamiltonian, just disorder.
Yeah.
You can partition the lattice into sites with random phase 0, right? Some sites have random phase 0. And I can connect them if they are nearest neighbors. So then I would have a graph.
Yeah.
This problem is a site percolation problem, and which has been studied very, mathematicians in the 80s, 90s, or
Sure.
So in that sense, mathematicians have proven that these percolation systems are fractal-like. The boundary is proportional to their volume. So even without a Hamiltonian or anything, the disorder itself has a site percolation, an innate site percolation problem. It's just whether the ordering is connected to the site percolation is another question.
I see. Yeah, so it looks like some how to express this, like this means that although like your order only localizes on the domain wall, because domain wall percolates, it spreads the order parameters throughout the system in this way.
Yes. So like if I were to choose two lattice sites on my cubic lattice, they're going to be correlated, but not correlated like through the bulk. They're going to be correlated through these boundary terms, like along two infinite clusters.
Yeah, but because of 0-1 theorem, like if it percolates, it always can be connected with almost one probability. Is that true?
Well, with non-zero probability.
Well, non-zero probability.
Yes, exactly.
Okay. Sure. Thanks.
Can you also say like why is it hard to see this in numerics? Can't we just set up some classical Monte Carlo simulation of the two copies of XY model coupled with random disorder intercoupling?
So it's easy to see it in numerics if it's 3 dimensions and above. But the problem was whether 2D systems can be infinitely stable or not, right? So the argument goes as follows, right? Each cluster has ordering. And so what you want to look at is whether the relative orientation has ordering or not. Now, if each cluster has long range ordered, then the relative orientation should also be long range ordered. But in 2D systems, each cluster is only quasi long range ordered. But can the relative orientation be truly long range ordered? That's the question here. So clusters are long range ordered, but relative orientation, clusters are quasi long range ordered, but relative orientation, can they be long range ordered? That's the question.
I see.
Wait, so people already see this, I guess, in 3D simulations, or can people do these simulations in 3D, like on bilayer?
In 3 dimensions, there's nothing really to see, right? It's just long range order.
Well, you could imagine seeing your lower plot here as a function of disorder.
Yes. Yeah. So the thing is that people haven't really studied this disordered system that much. There's no reason to believe that, at least before this talk, I don't think there's any reason to believe that there's ordering at large disorder.
Okay, other questions? All right, so let's thank Andrew again.
Thank you for listening.